Hello, everyone. My name is Ashish Darbari, and I'm founder and CEO of Aximize. And I'm really sorry I couldn't be with you in person in India due to some unforeseen circumstances on our end. But nevertheless, I am absolutely happy that I am able to take you on a 90-minute journey into the fascinating world of formal methods. And we are going to start today by taking the first steps towards verifying billion gate designs with formal methods. I'm going to show you how to start your journey with formal, and you can take it all the way to verifying very big designs. So, who are we? Well, we love signing off designs with formal. We are formal verification engineers and professionals who are actually helping customers sign off chips with formal and doing a lot of training. But let me not jump the gun and tell you in a second. So first of all, who I am. Okay, this is a very good question. I'm still trying to figure that one out. I studied and worked in 3 continents and 5 countries. It's something that's not very easy to get. I was very lucky. Before starting Aximize, I was the head of the product team at OneSpin Solutions in Germany. And prior to that, I was leading the advanced verification methodologies group at Imagination Technologies in Kings Langley in the UK, where I ran formal verification services and training effort across all business divisions of Imagination. I was also at General Motors in Bangalore for a year, and I also spent time at ARM, where I was pioneering a lot of the early formal methods work, and also had a stint at Intel. I happen to have a PhD in computer science. It's with the focus on formal verification. The whole PhD was on problem reduction strategies for model checking. That was at Oxford many years ago. I was also a visiting professor at University of Southampton, so I've always maintained close links with academic research and teaching activities. I've always been very passionate about both sides. I have a very active background in theorem proving. I still, till date, run proofs with theorem provers. Very active user of property checking and equivalence checking. I have a number of publications and also very keen at innovations of 60 patents in formal verification. Why I'm telling you all of this is because I started my career in electrical engineering back in Birla Institute of Technology, Mesra. So coming from electrical engineering and moving into formal methods and being able to carve out a career has been a lot of joy and fun. And I would highly encourage a lot of you who may not have had a background in computer science or formal methods at university to consider taking that leap. It is a lot of good fun. Okay, so what are we doing at Aximize? We're making formal normal. We have a number of ways of making this happen. We have products, we have papers that we publish regularly, a lot of online content, blogs, and podcasts. So the whole idea, the whole vision of Aximize was that we want to make formal mainstream and want to make it as normal as all the other verification paradigms that you keep hearing and using. And the thing that is missing always from a formal verification execution has been the predictability. So we want to enable predictable formal verification and want to make everyone adept in formal. Adept is also an acronym of an agile formal verification flow that I invented at Aximize some years ago, and I'll be talking about that today. So what are the solutions and how are we making formal normal? So we have a 4-pronged approach. We always been very passionate about training. I have always been training before I started Aximize, but equally training was at the center of this rollout. We have many different training programs. We have instructor-led programs, face-to-face programs, and a lot of companies in the industry have taken these training programs. They go all the way from primers to completely comprehensive methodology-based. The important thing to understand here is we are actually teaching you how to do problem solving in a tool-independent manner. So there is no real dependency on one particular tool vendor. A lot of the business, the core of the business is consulting and services, where we are actually taking on projects in-house and verifying them and signing them off completely end-to-end with formal weekly updates, verification strategy, planning, coverage, the usual flow for formal. We are applying it on very, very complex projects. And this is the core of the business. And then to make things easy for certain domains, specifically for RISC-V, we have developed a very cool set of solutions, apps, that actually allow us to automatically verify the processors without having to learn formal. So if you haven't got staff to teach, then you could actually take this app and apply this on a RISC-V processor and find tons of bugs, architectural and micro-architectural. And I'm going to give you some insights on the kind of bugs that we have been able to find through this effort. So the idea in all of this is focus on bug hunting, but also focus on building exhaustive proofs. So the last 2.5 decades of my life have been spent in pioneering methods and technology that can be used to apply formal in a very scalable way. Okay, so formal verification at scale, as I said, turnkey services delivered on some of the projects. And as I mentioned, functional verification of designs have been carried out with over 1 billion gates with formal. And the core of this is abstraction, something I'm going to cover in this tutorial today. We're also helping customers with post-silicon issues on designs previously verified by others. So if you have an AI/ML accelerator chip, talk to us. We could do a great job with formal verification. If you have a NoC, if you have an Ethernet switch, low power chip, mixed signal, power controllers, DMA controller, multi-threaded processor, bus bridges, using any of these protocols, cache subsystems, GPU blocks, any of the SoC peripheral IPs, we have the experience of carrying out formal verification on all of these. So I just wanted to give you an idea of the scope of formal as to how wide it is, and there's really no limit to where we can go with this. So what do customers say about us? So this is a very kind endorsement from AMD, where they mentioned that our FV experts have a deep understanding of formal verification at an engineering level, including the balancing act between fast-changing RTL and changing requirements. And they say that we are experts at deploying formal methods for large-scale design verification. Not only in the commercial space, we are also interacting with the open source effort that is going on in the industry. And I personally carried out a lot of work with the Open Hardware Group on the CV32E40P processor, which has now been taped out in a board and has been in the news recently. And Rick O'Connor was very kind to say these words for us. Where we have not been able to persuade the customers to allow us to name them, they have been able to say things anonymously. And what is interesting is you would find that in all of these, the emphasis has always been on how we handle the customer project. So for example, in this case, I was told that I was quite patient, something I'm not particularly good at, but I was told I was very patient and very good at handling the teaching side. And although this particular customer had a lot of background in the theory of formal, he was totally not aware about the proof engineering effort and how do you do breakdown of a complex problem and how do you apply concepts of theorem proving into property checking. So this is how I help them do this. So for more testimonials, if you're interested to know what we've been up to, please check out this link and you'd be happy to see what customers are saying for training, for example. Right. So we have been not just doing project work or delivering training, we've been actively delivering free online training and knowledge base and know-how through multiple different platforms. So through YouTube, you can go and find a lot of videos that are on the technical side of formal application, methodology space, and all of this is for free. It is for you to be able to sample what is possible with formal. Right, so why are we doing formal? Why are we even here? Why do we want to spend the 90 minutes trying to learn something, right? Why don't we just use simulation? So let me try and make my case. So here is the industry's report card compiled on the basis of using the Wilson Research Report from 2020 and 2022 by none other than Harry Foster. And you would find here it's very deeply insightful. There are a lot of things that haven't changed. For example, 66% of the IC ASIC projects continue to run behind schedule. 76% of the IC ASIC designs continue to go through respins in 2020. 60 to 80% of the overall verification cost, right? That is the cost of your project where it is being spent in verification, 60 to 80%. Even FPGA designs are not doing very well. And what you'll find here is that in the logic and functional flaws that are causing respins in designs with over 1 billion gates, that's pretty much anything and everything from an iPhone to a laptop or a server class chip. 62% of these bugs are actually logic functional flaws. And I have personal experience of seeing a lot of variety or flavors of these in projects that we look at, which have been either missed previously in the previous generation of the projects or are not getting picked up by UVM test benches. And no matter whether you do 10 to the power 15 simulation cycles, functional bug escapes are becoming a norm in the industry, which is rather shameful. And as the time to market is continuing to shrink, as we are rushing towards the next AI chip that is going to give you the next generation of ChatGPT or the next 5G, 6G technology, or chips that are going to be driving our cars, we just cannot afford to be complacent and cannot move with the mindset that all is well. So no matter what you do, you have to take a step back and ask yourself, are we doing enough? If you look at the classic Intel FDiff bug, that was itself quite a big event that shaped up how Intel looked at verification, specifically formal, to the blow up of Arien 5 in mid-90s, to the meltdown, Spectre, and Pacman issues in security. Catastrophes have been happening. I mean, this is not even a complete list. This is just a sample of some of the well-known ones. As more and more companies get empowered by open source ecosystem, and they're going to be building new chips that are going to end up in our embedded systems in the IoT space, we need to do a much better job at verification. And folks, formal verification is here to make that happen with faster turnaround time, higher quality bugs to be found, and more importantly, you don't have to actually leave anything on just guesses. We can actually prove that the bugs don't exist. So why is verification hard? It's not just functional verification. So let me tell you, if you're on an SoC team, you're looking at a front-end SoC team, you're talking about functional verification plan, safety verification plan, compliance with ISO 26262, security, compliance with emerging security standards. You want to make sure your PPA, power, performance, and area is up to the mark. So you're looking at different things in a different way. Some people using virtual platforms for performance modeling. People are trying out different high-level modeling techniques to make sure the performance is up to the mark. But when they're doing that, they're not looking at safety. They're not necessarily looking at security, Functional verification is always considered to be the most important verification task, and people are totally fixated with the way they look at it. If you were on the back end, you'll be doing clock domain crossing, you'll be doing reset domain crossing, timing, synthesis, layout. All of these are very important tasks that enable the SoC to leave the house. However, my concern is that when we are attacking all of these tasks, we are not looking at them in a holistic way. So what I'm trying to say here is that a lot of these issues overlap in the way they affect each other. So if you have a deadlock at the microarchitecture level, it is possible it will end up causing an architectural issue in the chip. If you have a power issue, it may actually cause a deadlock. For example, you may have put X's to enable low power. That can itself cause deadlock both at the microarchitecture or the architecture level. This can cause problems with functional safety lockstep. This can cause vulnerabilities in confidentiality, integrity, and availability, causing you security issues. So they're all interconnected with one another. And there is some really awesome work that my team has done on showing that they're all connected to each other in the context of RISC-V. There have been numerous papers we have published. So please contact us at info@aximize.com, and we'll be happy to point you in the right direction. So what we're saying here is that a holistic approach is missing. What is missing is a connection from architecture to silicon in the way that whenever something is being verified at whatever abstraction level we are looking at, whether architecturally or microarchitecturally, we have to look at the interconnections and the overlapping concerns of these different verification goals. So you can't just look at one, you have to look at the whole. So why bugs escape to silicon? My view is that simulation, as great as it is and as widely used as it is, the central conundrum with simulation is stimulus. And too many dependencies and scenarios to cover exhaustively with simulation. I'll give you an example, right, in a second. So conventional verification of processors relies heavily on architectural testing. Unit level testing, yeah, everybody does it. Create directed tests and check for a specific behavior. Does an add instruction work correctly? Does a subtraction instruction work correctly? UVM randomized testing came along with an amazing feature of random stimulus generation and being able to go and traverse certain states of the design that would otherwise not be possible with directed testing. I get that. But unit level testing is good for bring up testing, but isn't comprehensive. And you know what? Randomized testing can reveal corner case issues, no doubt about it, but it is not exhaustive and won't find you all your bugs. I think we have an agreement here, and most people would agree that functional coverage, therefore, is the main way of signing off if you were doing UVM alone. So bug escapes are inevitable. We see them all the time in the chips that we are verifying at Aximize with Formal. Our customers tell us to, so we know that this is a real problem. Now, if you look at the processors, for example, massively optimized, they have pipelining, they have interlocking, forwarding, they've got branches, they've got jump instructions, forward jumps, backward jumps, exception handling, stalls, interrupts, debug. Then you have extensions. So in the context of RISC-V, for example, extensions is a big deal. This is where small and medium-sized players are coming up with really crafty ways of optimizing power, increasing performance, minimizing area, clock gating, arithmetic checking. And you have power, safety, and security. Now, you can't just look at the world of unit-level testing and randomized stimulus generation to sign off a chip with such complex optimization. So simulation alone cannot verify all the scenarios exhaustively. I'll give you an example. Do interleaved instruction sequences always work as expected? Even for a small core, we're talking about 32 registers, say 60 plus user instructions. How about verifying that certain optimizations do not break the functionality? You have data forwarding here. Are you going to be writing one directed test? Are you going to be writing 1,000 directed tests? How many permutations of these instruction interleavings are you going to check? How many permutations of this operands are you going to be able to check? And this is not just for data forwarding. This is to make sure that other optimizations work correctly. So you understand that actually we are trying to, take the approach where we're trying to, find these bugs in a haystack, right? It's just not going to be very, very easy, and that's why things go wrong. Now, when you have complex control and data dependencies, and the cores have in-order and out-of-order behavior, so I'm talking about speculative branches, forward jumps, backward jumps, page size jumps, page boundary jumps, jumps across pages, same or different. There's so many different cases to consider, isn't it? So you can't, as a human being, come up with all scenarios of stimulus generation, which covers everything that you always wanted to verify as per the verification plan. If you're talking about caches, for example. You want to check the behavior of cache hits, what happens when cache miss happens, what happens if you have write-through stores, what happens if you have different kinds of loads and stores, for example, bypasses, atomics, what happens to cache coherency. So there's a lot to consider and think. So look at this example. For example, you have a load word followed by an add, followed by another load word. Now, what happens if the second load, this one, was issued out of order with respect to the add instruction? Now, if there was a bug in the microarchitecture that allowed the second load word to overtake the first one, then the second load will update register X1 incorrectly, causing the value of X1 to be passed incorrectly to the add instruction. So you may now run a directed test case with this combination. Then you may bring up a load byte. You may then bring up a load half word or a store. But what are we really trying to achieve here? How many different, gazillion combinations can you realistically check? And remember, you have to make sure that these registers are the same. You have dependency on this. Yes, you can have programs that can generate and automate the generation of these test cases. But where do you really draw a line is what I'm asking. So formal verification takes a very, very different approach to this, which I'll show you in the tutorial. And my question to you is, how many test cases will you write to check this case properly, or in general cover all such cases? And how many random tests will you run to check this? So I'm trying to explain to you when things get really hard. For example, this is a load value axiom from RISC-V. And what we're really saying is that if you have threads I, J, and K, if the thread I performs a store operation followed by thread J performing another store followed by thread K performing a load, then the value retrieved from the memory by the load will be the latest value updated by a store. So we formalize these things in fragments of higher order logic, in theorem provers, so that we can end up then extracting properties that look like this in SVA, which say that at boss edge of the clock, if you issue a load word aligned instruction, then 4 cycles later we get the expected value. And the beauty of writing assertions and running them in formal verification tools is that all possible instructions are being checked. Arbitrary interleavings of loads with other instructions are checked, and this is all done for you for free. We don't have to do anything by hand. And this is how all the different gazillion permutation combinations are automatically checked. And we create these properties so you don't have to go and do something like this. So in the world of property checking, we write things like this. In the world of theorem proving, we write things like that. We use theorem proving to articulate, formalize clearly the intent specified in specification documents in English, so that we have a very clear idea of what we would like the chip to have, and then we can write properties that can be verified with formal verification tool. So when you have complex control and data dependencies and the codes have in order or out of order behavior, I talked about this particular case. There is another case of the forward and backward branch case. The execution of the second branch is dependent on the outcome of the first branch, and the second branch execution uses the value of X4, which can change depending on whether we can execute the add instruction. And supposing the add was issued out of order, then the second branch can use this value. But if it wasn't, then the add may never be issued. So they're a very complex case of forward and backward branches here, and just iterating that no matter how you look at it, whether you're designing very simple processors or complex ones, you will run out of steam with the number of directed test cases or UVM test cases. So let's recap. What have we covered so far? So what I have shown you so far is why we should care about formal, why is verification hard, why bugs escape to silicon, why chips such as processors cannot be adequately verified by simulation-based techniques alone. So this is me trying to lay this ground for you to make you see why we have to look at formal in the first place. Now, what kind of bugs can be caught with formal? So let's do a quick run through some of the bugs that we have found on projects. So to begin with, here is the report card of some of the processors that Aximize has been involved in verifying in the RISC-V space. And you can see that even processors that were previously verified, like zero risky, very simple two-stage pipeline processors, there were about 77 bugs that I picked up. This was previously verified by UVM. In all cases, the amount of time it took me at runtime to find these bugs is less than 30 seconds. Microarchitectural bugs, deadlocks, and architectural. IBEX, another processor, same or similar results. CV32E40P, we found a bit less because I was also building the app at the same time. But nevertheless, in the case of Warp 5, it's very interesting. This was previously verified by Formal, not just simulation. And in fact, they had exclusively used Formal, some group using open source Formal. And I'll talk about some of the bugs that I picked up in these as to why they were actually missed previously. But what you will find here is that even if the processes are 6-stage in order pipeline, they're non-trivial. They are being exhaustively verified with Formal, and we are finding bugs. So let's take a look at some of the bugs we found. So I just wanted to point out Formaliza is one of the apps that we built, and we have deployed this on many different processor verification projects, and I want to now talk about some of this. So here is a bug report that I filed on IBEX, where I'm talking to Philip and telling him that all of the instructions that I had put under the scanner are actually broken, and actually, other than SLLI, SRAI, and SRLI, there's 3 shift instructions, all the other checks fail. And what exactly, so this is Philip accepting that this was an issue. So what exactly is happening is here. So let me explain this to you. What is going on in here is you have, let's say, a branch of equal to instruction in the pipe, and this got issued for decode, and the RS1, RS2 values were equal. So you were expecting the branch to have the normal behavior, which is that the next state of the program counter should be updated with the branch address. What happens is that this is where the BEQ was decoded and was sent for execution. But if during decode state, the FSM state in the processor, microarchitectural state, if a debug request arrived in the same clock cycle, then what happens is that all hell will break loose. So as a result, the PC will go in an exception state, and none of the instruction behaviors, not even the BEQ, would ever work correctly. Now, this is because there's nothing in the design to take care of such requests. And it took me less than a few seconds to find this bug once the app was kicked off. The processor design was compiled in Jasper Gold. The properties failed within a few seconds. So the thing is, this bug only ever happens when the debug arrives and the controller FSM is in the decode state. The precise timing of arrival of debug will make this bug really hard to catch in dynamic simulation. And we were able to catch it in 7 cycles. So how do I know that actually it isn't a problem in other states? And this is the cool thing with Formal. I was able to then construct a test case to say, let's say that the debug can arrive in all other states but decode. And because this was an input signal, I was able to constrain it to only happen in all other states but other than decode. If I was to apply this constraint in the Formal verification environment, then I was able to prove that all instructions would work correctly. And the design would happen to work correctly, or at least give you an illusion that it works correctly. So with Formal, the cool thing is not just being able to find these bugs, but also being able to prove the precise causality and the root cause behavior between the trigger and the effect. So this is an example of a security vulnerability found on CV32E40P. So here's what happens. So we have an e-break instruction that has just got issued, and the e-break instruction is triggered by debug, and therefore it has the highest priority. Now what's happening is, before the e-break got issued, in the cycles before that, there is a pending store instruction, And the store instruction is waiting to be completed because it has a dependency on data rvalid_i on the memory interface, and the rvalid_i isn't coming back. So the store is waiting for rvalid_i to come back to complete, and you have an e-break. Now e-break should flush out the store because it's a high priority privileged instruction, but the processor hasn't got anything in the code to make that happen. So as a result, the mcause register that needs to be updated with the requisite exception handling value cannot be updated. There is a deadlock, and we are stuck. And the reality of this is that this only ever happens if e-break is preceded by a load or a store. And again, I was able to prove this, that in all of the cases, e-break would work correctly, but in this case, it isn't. So, of course, the designer was arguing with me that because the rvalid_i is from the memory side, if that doesn't happen, then how do you expect the store to complete? And this isn't a problem of the core. I agree with that. The problem is, when you've issued a higher privilege instruction, it is supposed to flush and allow the lower privilege instructions to disappear. In this case, the load and store should be kicked out, but they don't. So imagine if this was a processor deployed in space, and you're trying to kick off a debug from here, and the debug is now blocked from executing because there was a problem with the memory interface in the first place. You're stuck. So you have to think about these issues in a fundamental way. This was all done as part of more extensive work which we presented in DAC 2021, Comprehensive Processor Security Verification, a CIA problem, where I was able to demonstrate that you can actually use formal verification to come up with security analysis at the architectural level, and we can annotate the vulnerabilities with a quantification value, which allows us to see how severe a particular security vulnerability really is. So moving on, this is an example of the load instruction not working on zero risk key many months after it was built. And here the problem was that by mistake they had left a custom reg load instruction sitting right behind the regular load. So during the multiplexing phase, the reg load was overtaking the regular load instructions behavior, which basically meant that load could not work correctly. Every single bug that I'm telling you about has been filed on GitHub, and you can go and look it up and come and talk to us. We'll point you in the right direction to go and find these. This is an example of WARP5, previously verified by Formal. And here is how things fail and why they fail. So for example, in the RISC-V ISA architectural document created by the RISC-V Foundation, it says that the JAL and the JALR instructions will generate an instruction address misaligned exception if the target address is not aligned to a 4-byte boundary. This was not implemented correctly, and this is because the designer was not sure of the semantics of what the specification said, and he went instead and looked at the guy who implemented the open source RISC-V formal test bench, and they had made a mistake as well. The designer copied the same idea, and due to a common mode problem, the bug was missed. So they were all filed on GitHub. There was an amazing intern, Shivani Shah, who came and worked for me for 6 weeks, where we found these issues. So there is then this one, BLTU doesn't raise trap correctly. This was an issue. AAUI PC was not working correctly. The div instruction is not working correctly. And you can see that a lot of these were in a range of different kind of bugs. It's not just the jump instructions or the division instruction. They were all over the place. So let me tell you about a bus protocol violation. This is a very interesting case. So what is happening here is that this is the AXI implementation used by the Pulp platform team. And we picked up a deadlock in this, and people have been using this for some time. I'm not sure why they haven't seen it. What's happened here is that if the AW and the W channels are busy, for example, right now you can see a constant stream of AW valid and AW ready, then what happens is that the AR ready will always be stuck at 0, and you can never have the AR channel ever getting a chance to get woken up. So this is a This is a deadlock that has been found by us and has been accepted. And what I'm trying to give you here is a flavor of the kind of issues we're picking up on designs that have been previously verified by simulation. And the fun in finding these bugs is that it doesn't even take us a lot of time to find these. It is literally a matter of taking our Axi protocol checker and bolting it on these IP implementations. So this is another very interesting B-response channel issue found by us. And the situation here is that the yellow part is showing that on the master side it is working correctly, on the slave side it isn't. So what's happening here is that the Axi slave protocol property says that if B response does not change in value while B valid is asserted waiting for B ready to go high, this is actually getting violated. So the yellow section shows 2 beats of the master Axi interface write response channel. The first beat is a single B valid and B response, and then a 2 cycle beat with B valid high on both cycles and B ready only high on the second cycle. So here the B response is behaving as expected, that is not changing its value, while B valid is asserted waiting for B ready to go high. However, in this section you can see the 2 beats on the slave Axi interface. First beat is a single B valid and B response, and then the second beat shows a 2 cycle beat with the B valid high on both cycles and B ready only high on the second cycle. B response changes its value in the second cycle, breaking the Axi protocol. So they're not necessarily very easy to reproduce in a simulation environment. I just want to point out this one. So let me tell you now about a very interesting bug found on a memory subsystem cache found by our app formalizer on a RISC-V processor. So here is the layout. Here's a processor is talking to the main memory via an MMU. There is a cache here, and there's a miss buffer. And what's actually going on here is that the cache lines are not getting validated correctly. There's an incorrect validation of cache line due to a bypass store, and that's what causes this to happen. So what's going on here is you have a load word request coming from a processor. It goes to the miss buffer for tracking, and you will notice that sometime later it goes to the memory to get executed. Now what happens is some cycles later you have a store word also to the same address that now makes its way to the memory, and this is a bypass store, so it has gone directly to the memory, bypassing the cache completely. And what is happening then is that the responses from the memory are coming back to the processor, and the values are coming back to the processor to say, okay, load word has finished, the value D1 has come back. And what's happening here is that the bypass store has updated the value of address A to D2. And the trouble is, because the caches hasn't been invalidated correctly, they're having the old value of D1. And when another load comes along, you can see that it finds a hit in the cache, and then the incorrect value is passed on to the core. This kind of bug is extremely difficult to find in a big design. And the reason is because you have so many different interacting players. You have the processor driving the main request. You've got caches being able to talk to the processor. The validation, invalidation has to happen. Then the miss buffer has to track the outstanding request. The main memory has to respond correctly. It's not just the logical flow that has to work correctly. The responses have to work correctly. And the quickest way to catch these kind of bugs is to write a formal property and run this on a design like this. But can formal build exhaustive proofs of bug absence is a question we want to ask, even though we can find bugs. And I've showed you about 12 different kinds of bugs that we have actually used formal for. So yes, there's complete democracy. This is a snapshot of verification of zero risk key and IBEX with all of the 4 tools in the market back in 2019. This is CV32E40P, 32-bit 4-stage in-order pipeline, extensively verified through Cadence Jasper Gold. This is a 6-stage in-order issue, out-of-order execution, in-order commit CVA6, quite a complex core. This has been extensively verified by us, again, using Cadence Jasper Gold. And And to give you a recap of where we are right now in this tutorial is we told you why formal was necessary, why verification was hard, why bugs escape to silicon, and why processes cannot be adequately verified by simulation. We are now at a point where we have also given you a flavor of what kind of bugs have been possible to find with formal. I don't want to give you any details about what formal verification really is without giving you enough evidence of why it is valuable. So I've shown you that we can find complex functional issues, we can find deadlocks, we can find security issues. So now moving on, let's talk about formal methods, a 30,000 feet view. So theorem proving, property checking, and equivalence checking are the foundational pins. If you are interested in learning about formal verification, we have, as I said, an amazing collection of courses on elearn.aximize.com. Sign up and you can actually get to see all these three technologies in action. So at a very high level, if I was to make you a 5-second pitch on what formal is, it consists of two things: specification and verification. Specification makes a description of the cause-effect relationship using a precise mathematical logic to make this happen. And the verification side is done by establishing a mathematical proof. You can use a theorem prover to build this proof semi-interactively. You can use a model checker or property checker. These names I was telling you: Cadence, Jasper Gold, Siemens, Questra, PropCheck, Synopsys, VC Formal. All of these tools are property checkers. They can then be used to build a mathematical proof.
I didn't get that.
So let's just describe what a property checking flow would really be. So here is a specification, and the specification comes from a requirements document. We take this to build an RTL. At the same time, we build properties which we split into three different classes: assertions, constraints, and covers. And we basically model it like this. Constraints are modeled through assume property, which means every passage of the clock enforce this expression. Assertions are modeled through assert property, which basically says every passage of the clock check that this is the case. And covers say, can you find me an instance where this expression may hold? Every passage of the clock keep checking. These properties are then most of the time coded by us, human beings, unless you are using an app like Formalizer where we've already coded it, or you're using a protocol checker where they come pre-compiled. They're then sent to a mathematical tool, formal verification tool, which builds a mathematical model of the design and the properties, and it comes up with a pass, fail, or a question mark answer. So if you have a pass, if you get a green tick in the tool, this means you have a proof. Sounds exciting, isn't it? But you have to be aware that there are no over constraints. In formal, you do not have to create a stimulus, but you may block a legal stimulus by mistake, by putting an assume property, or by making mistakes in the way you've modeled glue code. So you cannot have over constraints. That is something you've got to look at. And if you don't have that, then you do have a nice proof which says that the property and assertion is true on all input combinations on all reachable states of the design. What happens on a fail? Well, you could be lucky, you can have a bug in the design. Hey, great stuff. Or you could have a bug in the formalization of the design intent, property formalization bug. You may not have understood what you were actually trying to model. Maybe the specification was vague. It often is the case. Bug in the understanding of what the intent really is. The formalization itself was correct, but the intent was wrong. Or you could have a missing constraint in specifying what are the legal values allowed on the inputs. We often come across big projects where we encounter failures because we do not know entirely what is the behavior of all of the pins on the chip. And then we have to work with the designers to get this information out. And we do spend some time back and forth to tighten this flow. This is quite an obvious and natural artifact of working on practical projects with human beings. But remember, with formal, you get a stimulus for free, so you do need to ban the illegal stimulus. If you don't ban the illegal stimulus, you then have the case of a spurious failure, and spurious here means it's not a design bug. Right. Now, what happens when you have an unknown outcome? How do you deal with inconclusives? So you have to look at the constraints. You have to look at what is going on with your assumptions. You have to look at your assertions and covers. You're going to have to review your glue logic. I'm going to show you an example of how you code these glue logic assertions and covers and constraints on an example really soon. You then have to look at all of these techniques. I'm going to be pointing to you about black boxing, mutation, scenario splitting. I'm going to talk about some of these today. I'm going to talk about abstraction today. We will not be, unfortunately, able to go into invariance and assume guarantee today in the tutorial, but we'll be happy to come and teach you on another day or show you on projects that we work with you on. So the thing is, yes, there is a specification, there is a verification. Okay, we write properties, but is there a flow? Is there a blueprint that we can adopt? The answer is yes. We built this Adept Flow. A is for avoid bugs, D is for detect bugs, E is for erase bugs, and P is for prove bug absence and tape out without bugs. So what happens is you take your design, put it in a formal tool, just compile it in a formal tool, right? And what happens is you start finding reachability issues. The tool tells you some of the design lines are not reachable. It tells you that some of the flip-flops are not initialized. All of this is part of an auto check flow. It picks up 32-bit value being assigned to a 16-bit variable. That kind of an issue can be picked up. Overflow, underflow issues. Coverage, the structural coverage starts coming out the moment you compile the design. If you start seeing design lines or expressions already not reachable through structural coverage reports, you already know there is a problem in the design. You can start finding redundant code. All of this for free. You don't have to do a thing. You just have to compile it. And a lot of the projects don't even do this. They simulate it for a year, and then we take this design in-house for formal verification, and we're looking at 100 lint errors. So I would say please do this as the first step. Moving on, you want to write your constraints to be able to then avoid seeing spurious errors like I explained before. But now you can go and find your deadlocks. You can start writing your FSM checks. A lot of the tools already have FSM analysis that can give you insights about your FSM reachability, X propagation issues. Remember looking at this at the gate level, 1 year from now. No, you don't have to. You can start finding your X issues on day one. Live lock issues, reachability issues, again, you can continue to find it. Now, the thing is, once you move to the detect phase, you don't have to say, I can't go back to the avoid phase. You can still look at some of these issues here as well, because the design may be changing as well. However, this erase and proof phase is an interesting phase where we are doing full-on functional property checking with user-defined properties and constraints. And this is the topic of the tutorial that we are discussing today. How do we write these properties efficiently, correctly, so we erase bugs and we prove bug absence? And when you've done this all on all of your IP blocks, you can then do integration checking at the level of SOC, where you focus on CDC, interface-to-interface verification, reset analysis, register checking. A lot of these apps are actually powered by formal properties under the hood anyways. And if you don't want to use those apps, you can write your own properties. The point is that formal is being used in a continuous manner throughout the design life cycle. And this is a flow that should be deployed by every organization that is doing any silicon design. I am personally aware of some of the organizations that have taken versions of these flows and have built scripted flows inside. So I would highly recommend you come and talk to us about this. So I'm going to talk about erase and proof. So I want to talk about these three things called A, B, and C that would be helpful for you to do this kind of work on erasing the bugs and proving and taping out. So A is for abstraction, B is for bug hunting and building proofs of bug absence, and C is for coverage. And I'm going to show you how these three things can enable you to build high quality test benches that will be used not for small examples, but also big designs. So let's take a look at a small example first, shall we? FIFO. So here is a two-pointer implementation of the FIFO with input ports, clock, reset, data, push and pop. And on the output side, you've got output data and an empty flag. And internally, you have the pointers read and write, and you have an array where things are getting stored. And what we're really expecting to see is that if you send in a trace of values A, B, C, D, E, F, G, H, symbolic values, we expect to see them come out in the right order without losing the value, without reordering them without dropping them or duplicating them. Quite a simple concept, you know. This is how a typical interface will look like in Verilog, nothing too complicated. Everyone in the audience already knows this Verilog. FIFO verification, how do you verify one now? So you could use a reference model. If you were using UVM, you could use a linked list, and then you can track the value coming in the DUT in a separate container and then do a comparison. And that's how most simulation test benches work. In the case of formal, we can't use these linked list data structures because they're not synthesizable, and formal verification tools in commercial space require everything to be synthesizable. So you could use another FIFO, internal FIFO you may have in your projects. And you could use that, and then you can tie that FIFO inputs to the DUT FIFO and compare the outputs. And for smaller configurations, this might work, comparing the values even in formal. It doesn't scale, however, because then you're talking about a FIFO having some states and then another FIFO having the states, and then you have a cross product of those states. It's too much for a formal tool to be able to give you a conclusive outcome. So what would work if the designs are bigger? And the thing is, if I was to actually give you now a solution for a FIFO, you know, you've spent all this time sitting and listening to me. Have you just come here to learn how to verify a FIFO? Not really. The thing I'm about to tell you how to verify a FIFO will work for UARTs, USB, I2C, I2S, load store pipe, packers and packers in video devices, asynchronous FIFOs, NoCs, and things like arbiters and schedulers. I'll give you some of these examples as well. And you can verify all combinations of input values and say with 100% certainty that you haven't missed a bug. So the requirement for all serial devices is that ordering is correct, no duplication, data loss, and data corruption, and empty and full checks work correctly. There is always a counterpart of empty and full in all of the big designs that I've mentioned, the USBs and the I2Cs and so on. The thing I want to point out here is that the most difficult check is the data integrity check to verify. And this is why we are focusing a lot of the time today in teaching you how to focus on those things. Therefore, ordering is important to make sure you get it right. And the reason it is hard to verify this with formal is because of the sequential history that gets built in. As devices get deeper, you have a 4096D FIFO, you've got to actually look at a whole trace of incoming value before you can check the last value. So, abstraction to the rescue. What is abstraction? It takes many forms. I'm going to focus on data and temporal today. A classic technique, really, data abstraction, where we abstract away zeros and ones by a new Boolean symbol, and specification and subsequent computation by a formal tool is then done using a Boolean symbol. And the result of this data abstraction is a logarithmic reduction. So rather than dealing with zeros and ones, we just deal with symbols. Very much like how you write VHDL in Verilog, and you're not building truth tables, you're actually using signal names, you're using register names. That's pretty much what we are doing in the formal space. Sometimes we also use an X value to get data abstraction. We could use cut pointing and black boxing. I'll show you how to use this in one of the examples today. But temporal abstraction is fascinating because it's fundamental to scaling formal. The idea here is we don't sample the state of every signal on every clock edge. We only sample when certain key events are observed. By using these events to trigger observation of signals, we define observation windows. And then each observation window has a start and a stop state. This is the important bit. We can then define multiple observation windows depending on what signals we are tracking. And verification then really becomes an art of establishing constraints on these windows and proving assertions and covers on these windows. So the idea is create observation windows on non-deterministic sampling of values of some of the signals that are of interest, not all, and then making claim on the observation windows themselves. So, time to show you some code. How are observation windows created using start and stop conditions? How are observation windows created for symbolic data leading to abstraction? how much data needs to be observed when abstraction alone is not adequate to control proof complexity. So remember, in the world of formal, we will not send any input sequences. We let the formal tool exercise for free all input sequences. We don't write any stimulus. We just constrain out the illegal ones. We don't just track zeros and ones, we track symbols, right? Like we said in Verilog or VHDL we do. And the checking by the formal tool is completely symbolic. This is where, if you've never done formal and you're moving to formal for the first time, you may have to program your brain to think like this. So, what is the high-level concept of ordering? For any two data values sent into a DUT in a predetermined order, if they exit the DUT in the same order as they were sent in, then the DUT maintains ordering on the elements. So how about we say something like this? For any two symbolic values sent into a DUT in a predetermined order, if they exit the DUT in the same order as they were sent in, then the DUT maintains ordering on the elements. And if it is true for any two symbolic values, it is true for all values. Okay, let's be more precise. Maybe use a formal notation from logic. So if I was using Hall theorem prover, I would say for all D1 and D2, if D1 was sampled in before D2, D1 would be sampled out before D2. And this is exactly what I would write in Hall today. Now, I want to show you how you could verify a FIFO using this axiom, this assertion in property checking. Not in Hall, but in a property checker. So we do this by following this approach. We're going to track two arbitrary values, we call them watched values, D1 and D2, and we will send them in a particular order. D1 will be sent before D2, for example. You could send D2 before D1, it doesn't matter, but make sure you determine that order first. And then all you have to do is to check that they come out in the same order. So we're going to define these tracking and observation windows by using what we call as registers in Verilog. So we're going to come up with 4 registers: sample in D1, sample in D2, sampled out D1, sampled out D2. And all we are really saying is we're going to be tracking these non-deterministic watched values, arbitrary values D1 and D2. And that's all we're going to do to track the overall flow of data. So nothing too complicated here. We've just declared registers and wires here. You could use them as logic types if you fancy using more funky versions of system Verilog. We're going to define these arbitrary values D1 and D2. They have to be as wide as the data width. And we're now going to define these two stability assumptions. What they say here is that when D1 and D2 are being sampled in, before they are being sampled out, please keep the value stable during the sampling event. That's all these stability assumptions are doing. They are not saying that we are only ever going to sample a specific value of D1 and D2. In fact, a formal verification tool would sample and check all possible instances of D1 and D2, all possible data values. But during the sampling windows, those values cannot change. So this is why we need a stability assumption. And now what we're going to say is, when are we ready to sample in D1? That is the case when D1 appears to arrive on data I, the input data port, on a push of the FIFO, and that we have not seen the signal before. So we want to maintain a unique sampling event for the value D1. For D2, it's exactly the same. For the outside, we say when this value D1 appears on data O, and I had previously sampled this value into the FIFO, then on a read event, if D1 is on the data O output port, and I haven't read it out already, then I'm ready to sample out this unique value of D1, right? So we're creating these unique observation windows by making sure we haven't sampled in on the input side and we haven't sampled out on the output side. Having modeled these on the wires with very simple assign statements in Verilog, we can now write another simple fragment in Verilog, which looks like this, which says that these registers start off by being reset, and otherwise they get set and they are sticky. The ones they get set, they remain set by these triggers. So that's all there is to writing this code. And now we want to define the interface assumptions. So we want to say that we don't want to do a pop on an empty FIFO. So the driving logic of the FIFO should never read out of an empty FIFO. So we need to maintain this assumption. And we want to say that if the FIFO is full, you must not push it, not push a new data in unless you read in the same cycle. So this FIFO has a microarchitecture requirement which allows for simultaneous push and pops. So long as you have a push, so long as you have a pop, you can have a push, otherwise you can't. So moving on, the two other key things that we need is that if I haven't sampled in D1, I must not have sampled in D2. This is how we enforce that D1 comes before D2. And because these are registers, every time the sample in D1 register is not set, sample in D2 cannot be set. So this assumption forces D1 to come before D2. And this little fella here, which says that sample in D1 has to be followed by sample in D2, is an optional assumption which forces D2 to follow immediately behind D1, providing you with a dramatic decrease in runtime for the proofs. And it is not an over constraint either. So you can take this out and plug it in and you can test out this constraint is only for performance. So what is happening now is that you write an assertion saying, if I have sampled in D1 and I have sampled in D2, so those arbitrary washed values were sampled in. If I have not sampled out D1, it must be the case that I have not sampled out D2. This single assertion called AS_ordering is enough to catch all ordering related bugs, duplication, or data drop or data loss. So this end-to-end assertion is so powerful that you can apply it on many different flavors of bigger designs with similar kind of layout for your code. Right, so when we verify a FIFO as deep as 32,768, this is what Cadence Jasper Gold produces. The assertions are shown as being proven. The assumptions are all shown here. This is how typically a Cadence Jasper Gold tool snapshot looks like. And if we insert a bug, which I'm going to go into more details later on as well. So for example, here, if I have a bug where the read pointer is skipping so it goes start off from 0 and goes 1, 2, 3, 4, 5, 6, 7, and then suddenly there is a bug in the design, it skips to 9. If that bug was in your design, this property would catch it right away. Sample in D1 gets set here, sample in D2 gets set in the following clock cycle, and then D1 has not been sampled out, but D2 has been sampled out ahead of it, flagging an issue. That's how powerful this approach is. So let's do a recap quickly. What have we covered so far? So in the last section, I showed you a high-level overview of formal methods, getting started with formal modeling, abstraction, bug hunting, and building exhaustive proofs. I've shown you how to model some glue code using very simple Verilog, and how do you come up with modeling an end-to-end assertion, what kind of interface assumptions were required, were we able to get the proofs, were we able to pick up some of the bugs. But the real question is, have we done enough? Have we got the coverage? What about the C word? What are the coverage targets? What are the metrics for code coverage? What are the metrics for functional coverage? Are we blocking legal stimulus? Do we have enough checkers? Are our checkers verifying all interesting scenarios? What about over constraints? How do we know they're not there? So this section will explain to you how we actually use the Aximize's 6-dimensional coverage flow to make sure that our formal verification test bench is robust. So we'll start off with coverage targets. I'll show you how to do assertion coverage. I'll show you what we can do to ascertain checker completeness, over constraint analysis, how can we use property-driven design coverage, and how can we exploit what we call scenario coverage to obtain metrics. So some of it is qualitative, some of it is metrics oriented. You have a very nice blend of 6 dimensions to obtain an end-to-end sign-off. You can deploy this in your projects every single day. Coverage targets. So for FIFO, we already went through the verification plan. Ordering is correct, no duplication, data loss, or data corruption, empty and full checks. This is what will be used to build a verification plan and functional coverage plan, right? So for a design as small as FIFO, this is all you need to think about. Assertion coverage. When you run something in a tool, so this is Siemens's Quester prop check, you actually get a dashboard that shows you an ordering proof has been done, the assumptions were done. So this is an assertion coverage pass-fail result. What happens on a property-driven design coverage? So let me show you a very interesting thing. How can we use a tool capability, which is property-driven design coverage, to find holes in checkers? So let's assume that we only have written in the ordering check. We have not written the empty and full checks. This is Quester prop check showing observability coverage for the ordering property. And here you can see that it is reporting 82.4% coverage, not 100%. What is happening here is it has used this assertion to run. And when this assertion was running, it calculated which design lines were reached and were used in the proof of the property. And if certain design lines were not used, they are flagged as being not used. So this is, if you do a little zoom in, you can actually now see that it is telling you all of these lines that were actually not used or exercised during the proof of the assertion. So for example, it says there's nothing in the assertion for ordering that checks next empty. There's nothing on full. So for example, if this FIFO had a bug where instead of it being 4 deep, it was 2 deep, the ordering check would still pass. So really to find that bug, you need those checks on empty and full. So all this tool is now showing you here is all those lines in the design code that were not exercised. So this is the same thing. If I was using Cadence Jasper Gold, we get a similar dashboard. So this is prop check showing you all of these deficiencies in the test bench. So we are going to go and then add, for example, one empty to full check, which is saying that if I start from being in an empty state and then we have a sequence of a number of pushes but no pops, and as many as the depth of the FIFO, we'll end up getting a full FIFO. And the converse, if we start from full and we have pops but no pushes, as many as the depth of the FIFO, we get to the empty FIFO. I'm not suggesting they are the best checks for empty and full. You could write different checks using counters to track push and pops, and those checks would also be very nice to write. Having written these two additional properties in the ordering check, the property dashboard looks like this. And now what you will see is it is reporting 100% coverage. So this kind of property-driven coverage is a very nice and quick way to understand if you may be missing obvious checks in your test bench. And this is what I use it for. So if you have reachability and observability, then you have full formal coverage. Reachability basically means that in the absence of formal verification test bench, all the design lines were reachable. If you brought in formal verification test bench, for example, constraints, and you were blocking the reachability of some of the design lines, we will catch those issues with reachability coverage. But observability coverage, on the other hand, gives you insights on what assertions were actually exercising which design lines. So this is the best combination of structural and functional coverage, all in a single unit of view. So this is why I love this so much. Checker completeness, then another way to do this is through mutation-based analysis. So let me show you. This is what we do daily in our projects when we're looking at big designs. So on a FIFO type examples, you can come up with a lot of different design mutations. For example, this one says I'm incrementing the right pointers on a push and decrementing it on a pop rather than incrementing it. So what happens if you, for example, plug this mutation in the design? Very quickly you will see that this property fails. You can see what is coming out from the tools is you have a sampled in D1 and sampled in D2. D1 is 3 and D2 is 1. Watched value is chosen to be 3 and is written at index 1 in the data array pointed to by right pointer, which is here. D2, which is 1, is written at index 2. Yeah. But when they are being read, because they're getting read in the wrong order as the read pointer is getting decremented, it causes the sampled out D2 to get set before sampled out D1. So in a 6 to 7 cycle trace, you're able to quickly check that your bugs are getting picked up by your verification properties. This is a really quick way and a very robust way of picking up issues in your formal verification test bench. At the same time, let's look at this specific mutation. So instead of having this line in the design where I have next read pointer equal to next write pointer, I went and inserted this mutation where I changed the next write pointer to W pointer. Next write pointer is effectively write pointer plus push I. So when I insert this mutation, hey, look what happens. This mutation is undetected. I threw the ordering property in the formal tool, and look, we have a proof that you just cannot detect this mutation. Oh dear, is there a problem then? Do I have a bad test bench? Let's dig into this a bit more. So we believe the checkers are correct and complete and there are no over constraints. That's what I'm believing in right now. This is the original code, this is the mutated code. So let's see what happens. So what if we make the following design change and I bring this expression as an OR term in this line and make this new next empty, which has now taken an OR of these terms. Let's see if we can show that this new proposal is safe. Does the design work the same way as it was doing before? And lo and behold, when we run this checker, we get a proof again. That means the ordering property is working correctly or not, I don't know, but there is a proof, which means that these design changes do not affect the design functionality in the way that they would break the ordering property. So the question is, can we now run coverage? And when we run the coverage with empty and full checks, we get 100% coverage. So the tool is not even telling me anything either, that there is anything wrong with the formal test bench. Maybe there is nothing wrong with the test bench either. We just don't know right now. So what happens now is we have this term, which was originally in the design. We then mutated it and modified it to be this one. How about we actually do some analysis and see if these two are the same? Do they always behave in the same way? Are they identical? Or in a formal world, are they equivalent? So there is this assertion I can write that if you have next empty, then it means next empty 1, or next empty 1 implies next empty. Now, you could of course write this assertion, which basically says, are they the same term, semantically equal, using equal to operator, it's the same thing. I'm just showing you another way of modeling this equivalence. And in all cases, you get these to be equal. So actually, the tool has now just helped me figure it out that they are the same thing. There is no difference between them. Every single instance of 0 and 1 assignment on this will produce the same result as 0 and 1 assignment on this. This is good. So now we know that actually we're getting close to understanding that they might be both identical, and that's why the ordering property didn't fail. So can we actually catch them now? So if we now go and insert a mutation on this one, and instead of equal to, I said not equal to, and we see right away one of the assertions full to empty has failed. If I now insert a mutation here, then I see the ordering check fail. If I now insert a mutation here, other properties full to empty has failed. So my properties in the test bench are picking up mutations, which means it's a good thing that the changes we originally made in this slide, they seem to be working correct. So this is a good one. Fine, let's keep it. But the question is this the correct modification? Do we need this OR term? Because remember, building an OR means building more area, building more logic, right? So maybe bad for power. This may not be the only FIFO in the design. There may be 5,000 or 50,000 of these in your design. And every single time you're putting an OR, it may be creating more problems for you in terms of logic and area. So actually, because this expression is equivalent to this expression, which one should I really use? Should I use this one, or this or this? So my take is we can actually check all of this. They are equivalent behaviors. What I suggest we do is we keep this implementation, not the one with next write pointer, because we have shown they are equivalent. And that's because that your next write pointer has an additional addition instruction. Next write pointer is write pointer plus push I. We don't need that. So we don't need that extra bit of hardware unnecessarily. So what I'm showing you here is an example of finding power issues, area issues, through logical analysis of test bench, through coverage on a formal test bench. So I hope this all makes sense. And you can see that if I now replace so next empty was meant to be next read pointer is equal to W pointer, but I've now inserted a mutation, and you can see it's such a strong, good design change that if we were to have a bug in here, straight away it gets picked up by our properties. And the right change to have in the design is have this expression for next empty, and then keep your existing test bench as it is. Right, so checker completeness. What happens if you have a bounded proof? So I don't like this word bounded proof because it suggests we have a proof, but we actually don't. So here is an ordering property on a very deep FIFO, 256 deep, 2-bit wide data, ran it in Quester prop check in 17 minutes. The proof was inconclusive. The coverage was 100%. Now, does it mean that you are done? Not really. So don't use these property-driven coverage results to make a final judgment call on sign-off. Use them as guides to find out gaps. Now, what if there is a bug beyond a bound? Don't believe in all this rubbish stuff that says that if you have a bounded proof, you are done and you can calculate these bounds and there is always a science to do it. There is no science. We are picking up projects where people have done this kind of stuff and we're finding bugs beyond those bounds. So what if there is really a bound? So imagine there is a bug now. The bug is that when the counter reaches 256, the reorder register gets set to 1. So this is a bug that has been planted in the design. Reorder is a flop. And when this reorder gets set to 1, the values will be reordered in the sense that data at W pointer plus 1 would be brought back to W pointer. So we just introduced this bug. Otherwise, the FIFO doesn't see this bug. And now you are not able to find this bug very easily. And that's because now you have, you have a reorder here thing, you have a counter here as well. So what we're going to do here now is because this counter has to count to 256, it's now going to cause 256 cycles of delay before you can find this bug. So when you have counters in the direct cone of influence, a thing to consider at this point is what I called black boxing or cut pointing. Now, cut pointing here is being applied because this black boxing is referred to a term when you black box the entire design block. Here we are actually going to take away a signal. The way we're going to take away the signal is multiple ways. We can either come up with not with techniques using just like a cut point in a tool that will automatically not drive the value with the way it is modeled in the design, or you could also then remodel the counter by providing it with an arbitrary jump in the increment value. In this case, I simply cut this counter, I comment this in the design. Now this count signal is completely undriven. If it is completely undriven, the formal tool will be able to drive it with any value. And when it does it, what happens is it creates a point of failure very close to the bug point, because now the counter would be forced to go to 256, 255, and then it is going to show you that reorder can get set, which means it will cause the bug to manifest. And you will see that in 1 minute, 14 seconds on a 4096 deep FIFO with 256-bit wide data, we're able to fail the ordering property and find a bug. Where exactly do you apply cut pointing very much depends on where these counters are sitting. It requires you to have a very careful understanding of the microarchitecture. I am not a very big fan of cut pointing and black boxing. Therefore, however, I also acknowledge that at certain times we do need them. And this is a good example to show you where you might need them. Over constraint analysis. So let's take a look at this assumption. So this was the one I showed you, that if you are full, you mustn't push unless you can pop in the same cycle. Now imagine if an engineer made a mistake and says, if you're full, then don't do a push. So it doesn't allow for a concurrent read in the same cycle. If that was to be the case, your properties would exhaustively prove, your coverage reported by the tool would be 100%, and you would have no way of finding that you have a problem with constraints. And here is where scenario coverage comes really handy, where you can use it to detect over constraints. So how about we write a cover property to say, hang on a second, the designer always told us the spec that push and pops can happen concurrently. So can they happen when the FIFO is full? So we write this cover. In the same cycle you are full, can you have push and pop? We write additional covers. For example, you could write, if I'm full, can I have a push and pop for 2 consecutive cycles? Just an additional sanity checking. And can we have it 1 cycle later? If I'm full now, can I happen 1 cycle later? Can I have a push and a pop? Some interesting scenarios. What happens is right away, your first 2 scenarios fail in the tool, and you are able to see that you can't have push and pop simultaneously. You can straight away go ahead and now fix this assumption. So now we fix this assumption to become the correct one, take away this over constraint, and now the scenarios are a pass. So by using very simple techniques of modeling scenarios through cover properties, or sometimes even with assertions, you can actually pick up constraint issues very easily. And results are consistent across different tools for scenario coverage. That's why I designed all of this flow on projects. And Cadence Jasper Gold, you can see the same problems. This is an over constraint. Then you can see that Jasper will also show you failing cover and show you reduced coverage. And then you can fix it and you get the right scenario covers, and the coverage also improves. So the storyline is similar, but now the insights that you have to get is to do the extra work of creating these scenarios. So just to recap, what have we covered so far? In the last section, we have showed you a 6-dimensional coverage for sign-off, missing checks, property-driven coverage, mutation issues. When you put in mutation, can you pick up design issues, test bench issues, uncovering issues in designs for area and low power, and how to detect over constraints using scenarios. So previously we covered the modeling part, and prior to that we showed you why formal, why bugs get missed, and how to catch what kind of corner case bugs were possible to catch with formal. So I hope you're still with me. Now, what about bigger designs? Does this method scale? So what I've showed you for FIFO, does it work for bigger designs? So I'm going to show you 3 different case studies: memory subsystem arbiter, memory subsystem scheduler, and a network on chip fabric, just to give you some ideas on how these things scale. So this is some previous work done by myself and my team. We presented in Cadence Jasper user group in 2015. This is a memory subsystem arbiter. You have got multiple requesters all arbitrating towards the same cache banks. So the requesters are actually put in different groups. You've got tons of stallers, FIFOs, and registers, a lot of state in here. And what's going on here in terms of specifications is that if you are in this group R0 to R3, and if you are in this group R4 to R7, if requesters from 2 different groups were able to request the access from the same bank, anyone can win. There is no rule that this has to R4 has to be given the grant, or R0. There is no such rule like that. However, if there were requests originating on R0 back to back, then they have to be served back to back in the same order as they were sent on R0. And this is per requester per bank. So now the checks have to be coded in terms of pairs of requesters and banks. And what you can now do is apply the 2 transaction method I just showed you for FIFO to check for ordering correctness between this requester bank pair. Of course, you'll be doing this for all requester banks. However, if you have the case that you have R0 and R1 both competing for the same bank, in that case, the requester with the lower index would have priority over the one with the higher index. In this case, your 2 transaction method I just showed you for the FIFO would work nicely in the same way that sampled in D1 and sampled in D2, the flow. So in this case, R0 would be served before R1, R1 before R2. So you can code this again between requester and bank pairs. That's how you do the coding. And this is how your 2 transaction method would be used to code the priority checks. So this was coded for first come, first serve, priority order. And the strategy was to use per bank per requester view. 72 asserts were generated to check first come, first serve, all true within 1 to 3 hours. Priority ordering checked through case splits, and 11 additional assertions, cases per bank times 2 groups of requesters. pretty much extension of the two transaction based model. All assertions in this case were proven within 5 to 7 minutes, overall less than 1,000 lines of code for this. So if I now look at a memory subsystem scheduler, again, some work that I presented previously at Cadence Jasper user group, here what's happening is that transactions are serialized into the scheduler where they are cached. Hazards and dependencies are used to resolve the scheduling order of transactions, which can be issued out of order. Each transaction is tracked by an ordering mechanism, and the watch transaction is tracked out of the scheduler by its ordering mechanism, and the watch transaction is related to other transactions around it to build ordering and integrity properties. So we have this sequence of transactions all sending in the request. For all transactions, an ordering is associated. One of these in-flight transactions is selected, so arbitrary selection through the watched transaction business, pretty much how we were using it for the watch data in the FIFO. And the next state of the chosen transaction is determined based on the sets of bits stored in each of the older in-flight data structures. So that's the design aspect. And the property of interest that we are trying to prove is that if you have a watch transaction that is in flight and is valid, and the watch transaction's operation is a write, it is followed by another transaction which is now a read, so write had come before read, then what we're expecting to see is that write is before the read. So the flow here is the same as the two transaction method that we have just shown you for the FIFO. So you can see we are saying you have write and you have no read. So it's a similar kind of skeleton. And you can see that although the concept for the FIFO looked like it was only applicable for FIFO, in this case, we have just applied the same thing on a much bigger design. So what about network on chip? My favorite example. It's the backbone of modern day chips. Every AI/ML accelerator chip, every server class chip has a NoC. And the problem is deadlocks and live locks apart from functional correctness. So with liveness, the problem is if the network is empty and there is a message that needs to be injected, then the message will eventually be injected. Any message injected into the network is always consumed at the correct destination, that is for functional correctness. For starvation, any message will always get access to the resource it wants to acquire. For deadlock, no such a state should exist in the network where some messages get permanently blocked. For live lock, no such a state should exist in the network where some messages move around infinitely. So in order to verify a mesh topology, for example, what we're talking about is a connection of processing elements connected through routers. And it's a point-to-point connection between each router and a PE trying to send the data. So this could be a processor trying to snoop on the cache of another processor through a sequence of routing paths. So what we're really saying here is that if you were to build a point-to-point connection, if you build a suite of properties that ties off each router with every other router and use the two transaction method as the main skeleton for tracking the data flow, then you would be able to model the correctness of functional behavior as well as deadlocks in a very nice and seamless manner. So we were able to do this and use Cadence Jasper Gold. And what you can see here is that we had a bunch of properties that were called master E to E, and they were checking the entire word level behavior. And the design itself was very, very big. This particular design had a compiled footprint of 337 million flip-flops and over 1 billion gates. And what we were able to do with a design as big as that is that we were able to find bugs whenever they existed. And we were able to find some of them in about 100 seconds of runtime. So I just wanted to give you some idea of how these big design blocks would be verified using the conceptual FIFO formal verification test bench that I showed you. So we're now at a point where we have nearly finished this tutorial. I hope you enjoyed this. I hope you understood why we need formal, what kind of bugs are missed by other verification paradigms, and how formal verification can be used to find what kind of corner case bugs, what are the concepts of abstraction, bug hunting, proofs of bug absence, and coverage, how they can be used together to make sure your formal verification test bench is end-to-end, relevant for sign-off, can be used to find out any problems in the test bench, any of the 6-dimensional coverage techniques I've shown you. I would say start well by becoming skilled in abstraction. Use coverage in all its dimensions to verify end-to-end for sign-off. And remember the steps 1 to 6 and how they interact with each other. And understand these fundamental points. Go through this again and remind yourself of the key concepts. We are training, of course. As I said, go to elearn.aximize.com, sign up for a training course, ask your managers to get you signed up. We are, of course, working with production grade projects every day. So if you have projects where we can come and help you show how to find your first 5 bugs and the last 5 bugs with Formal, we'll be happy to do so and make you productive with Formal. And on that note, I would like to thank you very much for staying with me for 90 minutes. And do connect with us at info@aximize.com.